This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the discussion. Today we're delving into a research paper focusing on optimizing Retrieval Augmented Generation, RAG, using large language models, LLMs, on academic data. The authors explore several optimization techniques to enhance RAG's performance in a university setting. What are your initial thoughts on the core challenge this paper addresses?
The core challenge is bridging the gap between the general knowledge of LLMs and the need for domain-specific expertise. LLMs are powerful, but their knowledge is often not tailored to specific domains like university curricula. RAG aims to solve this by incorporating relevant domain-specific data into the LLM's context, improving the accuracy and relevance of its responses. The paper's focus on optimization techniques is crucial because simply adding domain data isn't enough. Efficient and effective retrieval and integration are key.
The paper mentions 4 optimization techniques: multi-query, child-parent retriever, ensemble retriever, and in-context learning. Let's start with multi-query. How does this approach improve retrieval?
Multi-query generates multiple variations of the user's original query. This is important because different phrasings can lead to the retrieval of different yet relevant pieces of information. By expanding the search space with semantically similar queries, the system increases its chances of finding the most pertinent information for answering the user's question accurately. It's a way to mitigate the limitations of a single, potentially ambiguous query.
The child-parent retriever seems interesting. Can you elaborate on its functionality and the rationale behind using different chunk sizes?
The child-parent retriever uses 2 vector stores, one for smaller 300-character child chunks, and another for larger 1,500-character parent chunks. Smaller chunks allow for more precise embeddings, capturing the nuances of individual sentences or phrases. However, smaller chunks lack context. The parent chunks provide that broader context. The system retrieves relevant child chunks and then uses their IDs to locate the corresponding parent chunks, ensuring both precision and contextual understanding.
The ensemble retriever combines BM25 and cosine similarity. What are the advantages of this hybrid approach?
BM25 focuses on exact term matches, while cosine similarity considers contextual relevance. Combining them allows the system to leverage the strengths of both methods. BM25 ensures that highly relevant documents containing the exact keywords are prioritized, while cosine similarity helps to capture documents that are semantically similar, even if they don't contain all the exact keywords. The weighting between the 2 methods can be adjusted to optimize performance for a specific dataset.
In-context learning is a common technique in LLMs. How is it applied in this RAG framework, and what are the challenges involved?
In-context learning provides a few example question-answer pairs as part of the prompt to the LLM. This allows the LLM to learn the task on the fly, adapting its response generation based on the provided examples. The challenge lies in selecting diverse and representative examples to avoid biasing the LLM toward specific aspects of the data. Poor example selection can lead to suboptimal performance.
The paper introduces a novel evaluation approach, the RAG confusion matrix. How does this differ from traditional confusion matrices, and what insights does it provide?
A traditional confusion matrix assesses the performance of a classification model. The RAG confusion matrix adapts this concept to evaluate both the retrieval and generation phases of a RAG system. It categorizes results into true positives, TP, true negatives, TN, false positives, FP, and false negatives, FN, considering both retrieval accuracy and the quality of the generated answer. This provides a more comprehensive evaluation than simply looking at retrieval accuracy alone. It helps to pinpoint weaknesses in either the retrieval or generation components.
The results show a significant performance increase when using multi-query. Can you elaborate on the magnitude of this improvement and its implications?
The results demonstrate a substantial improvement in the hit rate. The percentage of queries where the correct answer is among the top 5 retrieved documents when multi-query is included. The exact magnitude varies depending on the LLM and other optimization techniques used, but the improvement is consistently significant. This highlights the importance of exploring multiple query variations to improve retrieval effectiveness.
The paper also uses LLM-based evaluation, using GPT-4, for metrics like relevance, coherence, fluency, and faithfulness. Why is this approach used, and what are its limitations?
LLM-based evaluation offers a cost-effective alternative to human evaluation, especially when dealing with a large number of responses. GPT-4, being a powerful LLM, can assess these aspects reasonably well. However, it's crucial to remember that LLM evaluations are still a proxy for human judgment. There might be discrepancies between LLM and human assessments, particularly regarding nuances in meaning and context.
The paper compares open source, Llama 2, Mistral, and closed source, GPT 3.5, GPT-4 LLMs. What were the key differences in performance observed?
The closed source models, GPT 3.5 and GPT 4, generally outperformed the open source models, especially in the German language. This is likely due to the larger training data sets and potentially more sophisticated architectures of the closed source models. However, the open source model showed competitive performance in English, particularly when combined with the optimization techniques.
The paper mentions a discrepancy between LLM-based and human evaluation. Can you explain the nature of this discrepancy and its implications for evaluating RAG systems?
The study found that human evaluators tended to rate the responses lower than GPT-4. This suggests that while GPT-4 can assess aspects like fluency and coherence effectively, it might not fully capture the nuances of human judgment regarding relevance and faithfulness. This highlights the importance of incorporating human evaluation, at least for a subset of responses, to validate LLM-based evaluations and ensure that the system aligns with human expectations.
The authors optimized the pre-retrieval phase by allowing the LLM to freely predict the study program instead of constraining it to a predefined list. What impact did this have on performance?
This change led to an increase in the hit rate, indicating that allowing the LLM more flexibility in identifying the relevant study program improved the overall retrieval accuracy. This suggests that the initial constraints might have been overly restrictive, hindering the system's ability to find relevant information.
Looking at the Rouge and BERT score results, what insights can we glean about the quality of the generated answers?
Rouge and BERT score measure the overlap between the generated and reference answers. High scores indicate that the generated answers are similar to the reference answers in terms of content and phrasing. The results show that GPT-4 consistently achieves high scores on both metrics, indicating its ability to generate high-quality, accurate answers.
What are the key takeaways from this research, and what are some potential avenues for future work?
The key takeaway is that optimizing RAG systems requires a multifaceted approach, combining effective retrieval techniques with powerful LLMs. Multi-query significantly improves retrieval, while the ensemble retriever enhances the quality of generated answers. Future work could involve exploring more sophisticated retrieval methods, investigating the impact of different LLM architectures, and developing more robust evaluation metrics that better align with human judgment. Furthermore, expanding the dataset to include more diverse academic domains would strengthen the generalizability of the findings.
The paper highlights the importance of considering both retrieval and generation aspects when evaluating RAG systems. How can researchers ensure a balanced evaluation approach?
A balanced approach requires using metrics that assess both retrieval accuracy, for example, hit rate, mean average precision, and the quality of the generated answers, for example, LLM-based evaluations, human evaluations, Rouge, BERT score. The RAG confusion matrix, as proposed in the paper, is a step in this direction, providing a more holistic view of the system's performance. Researchers should carefully select metrics that are relevant to their specific application and consider the trade-offs between automated and human evaluation.
The use of both open source and closed source LLMs provides valuable insights into the trade-offs between accessibility and performance. What recommendations would you give to practitioners choosing an LLM for their RAG system?
The choice depends on the specific needs and constraints of the application. Closed source models like GPT-4 generally offer superior performance, but they come with costs and limitations regarding access and customization. Open source models provide greater flexibility and control, but might require more fine-tuning and optimization to achieve comparable performance. Practitioners should carefully weigh the trade-offs between performance, cost, and accessibility when making their selection. Experimentation with different models and optimization techniques is crucial to determine the optimal configuration for their specific use case.
The paper focuses on a university setting. How easily could these findings be generalized to other domains?
The core principles of RAG optimization, effective retrieval, and integration of domain-specific data are applicable across various domains. However, the specific optimization techniques and their effectiveness might vary depending on the characteristics of the data and the task. For example, the child-parent retriever, designed for handling structured data like university curricula, might not be as effective for unstructured data like news articles. Adapting the optimization techniques to the specific domain is crucial for achieving optimal performance.
The paper emphasizes the importance of data quality in building effective RAG systems. What strategies would you recommend for ensuring high-quality data for RAG applications?
Data quality is paramount. Strategies include careful data collection, cleaning, and pre-processing. This might involve manual curation, automated cleaning techniques, and the use of quality control checks. The choice of data representation, for example, vector embeddings, also significantly impacts performance. Regular evaluation and iterative refinement of the data are essential to ensure the ongoing quality and relevance of the data used in the RAG system.
The paper highlights the challenges of selecting appropriate examples for in-context learning. What best practices would you suggest for selecting effective examples?
Selecting diverse and representative examples is key. The example should cover a range of scenarios and complexities encountered in the target domain. Techniques like stratified sampling can help ensure that the examples are representative of the overall data distribution. It's also important to avoid examples that are too similar or that might bias the LLM towards specific aspects of the data. Experimentation and iterative refinement of the example selection process are crucial for optimizing the performance of in-context learning.
The paper's contribution extends beyond the technical aspects, also proposing a novel evaluation framework. What is the broader impact of this contribution to the field of RAG research?
The paper's contribution is twofold. It provides practical optimization techniques for enhancing RAG performance and introduces a novel evaluation framework that allows for a more comprehensive assessment of RAG systems. This holistic approach, combining optimization strategies with a robust evaluation framework, is crucial for advancing the field of RAG research. The proposed RAG confusion matrix offers a more nuanced understanding of the system's strengths and weaknesses, guiding future research and development efforts.
This has been a very insightful discussion on optimizing RAG systems. Thank you for sharing your expertise.